In the last lecture, we looked at the elastic scattering of X-rays first from an electron and then from an atom with multiple electrons. In this lecture, we're going to look at the scattering from a periodically repeating set of atoms, that is, from a crystal. You can find a lot of treatments of this material in the literature. There are many textbooks on crystallography. I'm going to be following the outline that's given in this book, X-ray Crystallography by Girolami from the University of Illinois. I'll admit that in teaching this part of the course, I had to go back and learn some things that I never learned as a student, and I did find Girolami's treatment to be one of the easier ones to follow. So the simplest possible crystal we can imagine would be a one-dimensional crystal with a single atom in the unit cell. Ideally, there would be an infinite number of atoms, but it would be sufficient just to think of it as a large number of atoms, and those atoms are equally spaced. What's going to be the interaction between this one-dimensional crystal and an incoming X-ray beam? Well, let's first of all think about the X-rays coming in at some arbitrary angle. Now, as we learned in the last lecture, the interaction between the atoms in this crystal and the X-rays is going to lead to scattering in all directions. But if this was the whole story, that the X-rays came in and the atoms radiated out X-rays of the same wavelength in all directions, that wouldn't be very useful. We could not figure out the structure of a crystal. We could not figure out the spacing or the geometry of atoms in a crystal from that kind of information. So there has to be something more to it. And that something more is the interference effects that arise because some X-rays are going to travel different distances than other X-rays. Remember in the last lecture we said if we have one photon that might have this oscillating sinusoidal repeat in its electric field, and then we had this photon interact with another X-ray photon of the same wavelength, but phase shifted by some amount. And what we learned is that the constructive or destructive interference between the two photons would depend on the phase shift. So if the phase shift were 90 degrees, we would get a wave whose amplitude is actually going to have the same maximum and minimum of both of the photons that are interfering. If we had a wave that was shifted by 150 degrees, we see that the amplitude of the wave has now been diminished, so there's more destructive interference than constructive interference. And then over on the right, we see the extremes of a 180 degree or pi phase shift, which leads to completely destructive interference. The waves cancel each other out. Or a 360 phase shift, or that would be 2 pi in radians, that leads to fully constructive interference. So when we think about diffraction from crystals, what we're looking for are certain directions of the X-ray through the crystal that lead to this fully constructive interference. And in the other directions, we're going to see varying amounts of destructive interference. Now, if you just have two X-rays interacting and they're a little bit off, or even maybe a lot off, like these images on the left here, it doesn't totally cancel each other out. But now if you were to have 1,000 or 1,000,000 X-rays that were all interfering with one another, and they're all off just a little bit, you don't have to get very far out of the fully constructive condition until you get the X-rays almost completely canceling each other. So where we see diffraction peaks in a pattern is going to be angles where we can maintain this fully constructive interference between different X-rays that are being scattered by different atoms in the crystal. All right, let's go back to our line of atoms, our one-dimensional crystal. Let's have one X-ray come in. We'll call this wave A. It comes in at a certain angle, and then we have wave B that comes in parallel and in phase, but scattering off a different atom in our crystal. We need to define some geometric parameters here. We can say that the spacing between atoms in the crystal is A, right? And because it's a one-dimensional crystal, all of the atoms are going to be this distance apart. We can say that the angle that the incoming X-ray beam makes with this row of scatterers is theta 1. And then the angle that the scattered beam makes with the row of scatterers is theta 2. And theta 1 and theta 2 are not necessarily equal. So what is going to be the interference effects, or the phase shift, if you will, between these two waves? Well, we can do a little trigonometry here. Let's define a right triangle here. And the significance of this dashed line is that the waves are in phase coming in. Okay, so their peaks are lined up, and they've traveled exactly the same distance until they get to this dashed line. But once they reach this dashed line, wave A is scattered elastically by this atom. Okay, so now it's on a different path. And the distance that's marked here with the red line, that's going to be the extra distance that wave B travels before it is scattered. On the scattering side, we can draw another line that is perpendicular to the waves, and this is another right triangle here. Wave A is going to travel an extra distance from 1 to 4 before they're back lined up with one another. So the difference in path length between wave B and wave A is the distance from 3 to 2. That's the extra distance that wave B travels, minus the distance from 1 to 4, which is the extra distance that wave A travels. Now, trigonometric relationships tell us that this red line here, right, this is a right triangle, and the hypotenuse of that triangle is A, the spacing between the atoms. So the length of this leg of the triangle is going to be the hypotenuse A times the cosine of theta 1. By the same token, if we look at the right triangle formed from 1, 2, and 4, we see that this blue line is going to be the hypotenuse A times the cosine of theta 2. So the path length difference is given here. A cosine theta 1 minus A cosine theta 2. And for constructive interference to occur, fully constructive interference, we want that path length difference to be a multiple of the wavelength. Of course, when theta 1 and theta 2 are equal, the path length difference goes to 0. And so in that case, we maintain full constructive interference. And that case would be something like this plane of atoms acting as a mirror. The scattering angle in and the scattering angle out, theta 1 and theta 2, are equal to one another. Now you might ask the question, well, could there be some other angles where we might get constructive interference because the path length difference could be 1 wavelength or 2 wavelengths? The answer is that can happen, provided that the wavelength is shorter than the spacing between the atoms. We'll come back to that later. But for now, the key point to think about is that when the angle in and the angle out are the same, we don't introduce a path length difference, and so we get constructive interference. Okay, now let's add a second plane of atoms, which is offset by this distance d. Now let's look at how these two rows of atoms will scatter X-rays. So let's have wave 1 come in at some angle theta and be scattered off an atom in the first plane. The angle that the incoming X-ray, which is represented by the unit vector S0, that's its direction, the angle it makes with the plane of atoms is theta. And then the scattered or diffracted X-ray, which follows this direction S, its angle is also theta. And we saw on the last slide that we're still going to have constructive interference when these two angles theta are the same. Now if we had another X-ray that would not scattered by the first row of atoms, but is scattered by an atom in the second row, or the second plane of atoms, its path would look like this. So the question becomes, what is the path length difference between these two X-rays? We're going to draw some right triangles here, right? So these dashed lines are, perpendicular to first the vectors S0 and here the vector S. And the path length difference, if it's equal to an integer number of wavelengths, is going to lead to constructive interference. So n here is just an integer, and lambda is the wavelength of the X-ray radiation. That path length difference on our diagram is the distance from 1 to 2 and 2 to 3. Now, a little trigonometry, though, tells us that if the hypotenuse of our triangle is d, the spacing between planes, if this angle is theta, then it means this angle also must be theta. And the length of this leg of the triangle then is going to be d times sine theta, right? Sine is the opposite over the hypotenuse if we have a right triangle. And so the total path length difference is going to be 2d sine theta. And if that equals an integer number of wavelengths, then we're going to get constructive interference. And this relationship, n lambda equals 2d sine theta, probably one of the more famous equations in science. This is called Bragg's law, named after the father and son team, the Braggs, who discovered this relationship in the early 20th century, and then used it to determine the structures of several simple crystals. We might also rearrange this, if we were so inclined, to say that the angle theta that satisfies this condition is the arc sine of n lambda divided by 2d. Let's go back to our one-dimensional crystal, this row of atoms that can scatter X-rays. And let's ask the question, are there any angles other than being reflected at the same angle that the beam comes in at that would lead to constructive interference? So for this derivation, we're going to allow the X-rays to be scattered not only in the backward reflection direction, but also in the forward transmission direction. And we've got some relationships here. So our incoming X-rays are coming at this angle with respect to our crystal. Right? Our crystal is vertical here. And the direction of the incoming X-rays is represented by the vector S naught. The angle which S naught is making to our crystal is we're going to call alpha naught. And then we're going to say that the scattered radiation is described by the unit vector S, and it makes an angle alpha with the crystal. And alpha naught and alpha are not necessarily equal. So under what conditions might we get constructive interference? Well, let's go back to this drawing of right triangles and use some trigonometry to figure out the path length difference. So the upper wave here, it travels an extra distance of 4 to 2 than the lower wave before it's scattered. And then after scattering, the lower wave travels this extra distance of 1 to 3. So the path length difference is simply the distance from 1 to 3 minus the distance from 4 to 2. Now, for constructive interference to occur, we need this path length difference to be an integer multiple of the wavelength. So we can write down an expression. H is just an integer times the wavelength. That's going to be equal to, this vector 1, 3 is just A, the distance between scatterers, which is the hypotenuse of this right triangle, times the cosine of the angle alpha. That's the scattering angle. The red vector is going to be, once again, A, still the hypotenuse of this triangle, times the cosine of alpha naught. If we know alpha naught, that is, we can control the angle that the incoming X-rays make with our crystal, and we could solve then for what is the angle alpha that would lead to constructive interference. First, we isolate the cosine alpha term on one side of the equation, and then if we take the arc cosine of this argument here, cosine of alpha naught plus h lambda over a. That is known as the Laue equation. And we can use this equation to see the angles at which constructive interference might occur when the X-rays pass through and are scattered by the atoms in our crystal. Let's look at the case where the incoming radiation is perpendicular to our crystal. So we can think of our crystal as being vertical, and the incoming radiation is traveling horizontally. In that case, the angle between the two, alpha naught, is equal to 90 degrees. So here's our Laue equation, and we can plug in 90 degrees for alpha naught, and then we can also specify the distance between the atoms, and this distance is going to be 2 times the wavelength of the radiation, 2 lambda. We're going to put those values in for alpha naught and A into our equation. Now the cosine of 90 is 0, and the lambdas cancel, so we're left with the angle or angles at which constructive interference occurs will be those that are given by the arc cosine of h over 2, where h is an integer. Well, what are the solutions to this equation? Are there an infinite number? Are there a finite number? Well, if h equals 0, then the angle would be 90 degrees. And that's, in a way, just the trivial result. That is, diffracted radiation is continuing on exactly the same path as the incoming radiation. All right? That makes a 90-degree angle with our crystal. What about if h equals 1? Well, in that case, we have the arc cosine of a half, and that's 60 degrees. So in that case, we can see that when the scattered radiation makes an angle of 30 degrees with the path that was coming in, we're going to get constructive interference. And if h equals minus 1, then we get an angle of 120. So we can see that these two beams, which are deflected either 30 degrees on either side of the direct beam, are going to give us constructive interference. Well, what about larger values of h? Well, if h is equal to 2, then we have the arc cosine of 1, and that's going to be 0 degrees. And if h equals minus 2, we would get 180 degrees. And so that's the vertical direction up and the vertical direction down in this diagram. They would be scattered along the row of atoms. Now, larger values of h are actually not going to give us any scattering, because if h were any larger, let's say like 3, then our solution would be arc cosine of 3/2. Well, the cosine function only goes up to 1, and so the arc cosine of anything bigger than 1 is not defined. And so what we see is we are only going to see diffraction effects if the spacing between the atoms here, between our scatterers, is larger than the wavelength of the radiation. So then you start to see why you need to use X-rays. You need to use some kind of electromagnetic radiation whose wavelength is comparable to, and ideally a little bit shorter than, the spacing between atoms in a crystal. And that's why we have to use X-rays. Now we could also look at this in another way. Let's say this incoming beam comes in, it's deflected at an angle of 30 degrees with respect to its original direction. That would be constructive interference. But there's not just one vector that makes an angle of 30 degrees with this initial vector. It could actually be scattered in all of the vectors that are pointing along this cone. Right? So we get a diffraction cone, all of which have h equal to 1 in that equation. We have another diffraction cone for h equals minus 1. And the scattering for h equals 0 could be anywhere in the plane that contains the incoming vector. So we get cones of diffraction along which we see constructive interference, and those cones radiate around the axis of our one-dimensional crystal. If we were to wrap a cylindrical detector around our crystal, we would see something like this. We would see dark lines. Let's say it was a photographic film, and we got a dark line anywhere that the X-ray radiation hit the film. Well, we would see a dark line at this point, and then we would see one up here. And if our detector were perfectly cylindrically curved, these would be straight lines. From our vertical crystal, we're going to get horizontal lines at which we're going to get constructive interference, and these are called the diffraction lines. let's increase the spacing of the atoms in our crystal. Remember in the last example that they were 2 lambda apart from one another. So if we keep the same wavelength of the radiation, but we make the spacing of the atoms 3 lambda, further apart by 50%, what happens to our diffraction pattern? Well, we start with the same Laue equation. And really the only difference is here where we're substituting the A, instead of putting 2 lambda, we now have 3 lambda. So we end up with alpha equals arc cosine of h over 3. Well, we still have a direct beam. That corresponds to this integer h being equal to 0. And that gives us an angle with respect to our crystal of 90 degrees. But when h equals 1 or minus 1, now we see we're taking the arc cosine of 1/3, and so we get an angle of either about 70 or about 110. So in the last crystal, the directions that gave us constructive interference were displaced from the direct beam by about 30 degrees. Now they're displaced by only about 20. We could make h equal 2 or h equal minus 2, and we would get 2 more cones of diffraction that have constructive interference. And only when we get to h equal 3 and h equal minus 3 do we get the solution, which is constructive interference straight up or straight down. So if we did the same experiment and had our cylindrical detector wrapped around our crystal, we would see more diffraction lines in our detector. Or another way to put it is we could say that the spacing between the diffraction lines has been decreased. The angles at which constructive interference are occurring have gotten smaller, and because of that, that means that we see for the same detector more diffraction lines. And this is a general property of diffraction. We see that as the distance between scatterers, between atoms, increases, the distance between the diffraction lines gets smaller. They're inversely related. And that's going to be critically important to understand diffraction as we go forward. So we can kind of summarize what we've learned about scattering from a one-dimensional crystal. First of all, we learned that constructive interference occurs along a series of nested cones, and those cones are nested around the axis of our one-dimensional crystal. We see that the number of cones depends upon the wavelength and the spacing of atoms in the crystal. And it will go up as the spacing between the atoms increases, as A, the unit cell length of our one-dimensional crystal, increases. And it's also going to go up as lambda decreases, so as the wavelength of the radiation gets smaller. And perhaps the most important fact is that the distance between the diffraction lines is inversely related to the spacing of the atoms in our one-dimensional crystal. A last thing we want to keep in mind, it'll be important in the next lecture, our crystal here is vertical, but the lines along which we get constructive interference are horizontal. So these are always perpendicular to one another. Now before we leave this, let's derive what is the more familiar form of Laues equation. We already worked this out, that the path length difference 1,3 minus 2,4 is given by this equation. But we could also express this in a vector notation. And to do that, we're going to take advantage of the dot product between two vectors. So if you have two vectors that are at some angle, if you have vector A and vector B, the dot product of the two is the magnitude of A times the magnitude of B times the cosine of the angle between them. So when the two vectors are parallel, the dot product is just the product of the magnitudes. When the two vectors are perpendicular, the dot product is 0. Now we can plug this back into the relationship up here, and we get A cosine alpha becomes the dot product of our vector A, that defines the spacing of atoms in our vertical crystal, times the vector S, which is a unit vector which represents the direction of the scattered radiation. minus the dot product of A times S naught. And S naught is a unit vector which describes the direction of the incoming radiation. Using the properties of vectors, we can rewrite this as A times the dot product of S minus S naught. This is the form of Laues equation that we will typically use. We could just kind of think about it for a minute here. S minus S naught is going to be a vector that's going to be in the vertical direction. And as that vector gets larger, then the dot product of it with A is going to get larger. And so there's only going to be certain times when that dot product is an integer multiple of the wavelength.